Hello there, my name is Will, and this particular workshop, this session, this video that I am broadcasting is part of my Learn DirectX11 Masterclass series. Probably leave a link somewhere if you're watching this on Instagram or YouTube. Leave a link somewhere if you want some more information about that. But long story cut short, I'm running a couple workshops. One being my Learn C Sharp Masterclass, which is being hosted primarily on YouTube and Telegram, but I'm also running my Learn DirectX 11 workshop, which, albeit the Learn DirectX 11 workshop has sort of kicked off a little bit late. I think it was August the 31st was the go live date of the workshop series, but effectively I started a little bit late. This is sort of like the official start, I suppose, and this particular workshop is going to be a gentle primer into what DirectX 11 is. What DirectX is used for, and the sort of functionalities and features you can expect from Direct3D11 API. So without much further ado, I'm going to jump straight into this workshop. It's going to be kind of a chilled format. Got my coffee on the ready, just in case if I need. And I've got my tablet display, which I'm going to be using for some visualization. And yeah, I'm just going to walk through some of the higher level concepts of what DirectX 11 is. Let's get straight into this. So what is DirectX 11? What is DirectX? Do excuse me. If you look on the right hand side, I do have some notes available as well. DirectX 11, or rather DirectX, is a set of graphics libraries that allows developers to develop fast, modern, and scalable 2D and 3D graphics for multimedia applications and video games. So, DirectX comes in a variety of versions. Let's see if I've got a good gauge for my brush here. That looks a little bit thin, so I'm going to just quickly make that thicker. Sorry guys, just to make sure that you guys can see what I'm writing a little bit easy. I'm going to put it on stroke width 4. Let's see if that's okay. Hopefully this is okay. So we have DirectX. So what is DirectX? Think of DirectX as a sort of umbrella, right? And under this umbrella of DirectX, you have a few libraries. Just as a bit of a heads up, this particular workshop does assume a novice space approach or a novice space level of experience that my audience, you guys might have with regards to DirectX. So, but with notwithstanding the fact there will be some assumptions, assuming that you have some fundamental understanding and knowledge of higher level programming concepts. But if there is any confusion regarding some of the terms that I use, please do let me know with feedback in the comments section so I know how to improve this series further. Alluding to what I said earlier about this being a workshop series, really it's about aiding your level of understanding and expertise and prowess with DirectX. So the interactive nature of these workshops is really what makes this really shine. So let's get straight into this. So under DirectX, we have some libraries, we have some features, some of which are Direct3D. We also have Direct2D. You also have DirectWrite. I'll say DW for now. Let's keep it at this for now. So what we're going to be looking at in this particular workshop is more or less the Direct3D library in terms of rendering 3D geometry and creating our scenes with DirectX. So DirectX is like the over-encompassing API, and you can consider Direct3D, Direct2D, and DirectWrite as different components of this overarching API. So Direct3D, as the name implies, helps us to render 3D based scenes. Direct2D helps us to render 2D based scenes, and the DirectWrite library helps us to write text, or helps us to render text and like sort of like typography on the screen. Okay, so stuff like that. I'm gonna save for this one. Okay, so why DirectX? What is the need for DirectX? Why do we even bother with a DirectX library or API if we have engines such as Unity, we have engines such as Unreal Engine that takes care of the main legwork? Why learn a language closer to the bare metal? And what was the whole concept behind DirectX in the first place? So the need for unification came about for graphics development or rather, the need for unification was sort of identified by a team at Microsoft around the 1995 era. Around the time of 1995, it was quite an interesting time for video games and 3D graphics. We were kind of coming out of or getting used to the post 16-bit era with 3D capable machines such as Sega Saturn, Nintendo 64, sort of being teased. I'm not sure if N64 was already announced by 95. I think it was. I think it was a 94 announcement with a launch a couple years later. And also we have the PlayStation at the time offering fast and at the time modern 3D capable graphics, 3D hardware. And a small group at Microsoft around this time of 95 thought to themselves, hey, look, we have all these hardware standards, we have all these development studios. Wouldn't it be neat if we could unify the toolset such that creating 3D graphics doesn't have to be such a proprietary process amongst different studios? And so when you think about it like that, then the idea of, say, let's see, so you might have, I was just talking earlier about how you had the N64, if I can even write 64 right there, N64, and you had PlayStation at the time, and let's just say Sega Saturn, right? Three different pieces of hardware for playing 3D based video games. And the N64 has its own set of architecture. The N64 has its own protocol, whereas the PlayStation 1 has a completely different set of hardware architecture, and the Sega Saturn having its own world of architecture. Of course, for those who know. And but then Microsoft had this neat idea. Okay, so we have this PC platform, right? What if the tool set for creating these 3D games exists on a sort of general level, such that if you use, so we have the 3D hardware, but between, let's say, the developer, accessing the PC, there's a layer right here. There's a layer like this. And this layer could be considered direct, let's say 3D for now. So when we develop via this layer here, we have access to the 3D hardware without having to fully comprehend the scope the scope of the 3D hardware layer. And if you think about it, if you make this direct 3D layer as thin as possible as a sort of interface between the 3D hardware and the application layer, then development is only easier, isn't it? Because you as a developer don't need to learn as much to utilize the scope of the 3D hardware. But that's notwithstanding the fact that DirectX as an API is quite vast. DirectX is rich, DirectX is robust. There's a lot to learn with the API. So it doesn't mean to say that this particular layer is quite lightweight. I would say DirectX is quite a full-on API. But that's the idea, isn't it? It's for this whole idea of unification for graphics tooling. So the era of Windows 95 and Windows Game SDK, now known as DirectX. So let's continue with this particular workshop. Let's go to the next section over there. I'm just going to refresh my screen. This is probably a little bit easier than hitting erase for all the vector brush strokes. So I'm just going to wait for my tooling to refresh. I will probably use the eraser tool next time. I think it's a little quicker. So anyway, I'm going to change my brush and we're going to get started with this. Excellent stuff. So the 3D rendering pipeline. The 3D rendering graphics pipeline is a set of stages that can be programmed and configured to process graphics from device input, graphics primitives, and buffer dimensions to polygons, texture, and rendered scenes onto a screen. So what is all this? This concept of the 3D rendering pipeline could be considered a search. So if we have here a pipeline starting from input, and for the sake of example, I'm gonna say keep this as a black box. Actually, it's not. It's actually not much of a black box. Let me rephrase this. So we have our input. Then we have a set of stages. So imagine we're inputting data into a pipeline. We have a set of stages. And then we have an output. So our input could be considered the base information, the base data. So this would be data used to basically create a scene. And then we have here our processes, our stage. Let's just number this, as you can see, as an example. And then we have our output, which at the end of the day, what we want is a scene. So let me change this. So scene info, something like that. And at the end, we want a rendered scene as such. And then we have this overall Direct3D, and in this case, we're going to be looking at Direct3D11 because there's many versions of DirectX and Direct3D. I think the most utilized version of DirectX is arguably DirectX11, which kind of was the de facto standard in its own right of the previous generation. If you're kind of looking at it, if you're looking at DirectX version 12 as the current gen. Excuse me. Okay, so if this is our pipeline and we have our stages, what are these stages exactly, and what do we need to understand to sort of comprehend these stages? Okay, cool. So that introduced, well, this kind of segues me into the discrete stages themselves, which I'm going to go stage by stage to describe. I'm going to just clear my screen very quickly. Alright. So we have a few stages, and I'm going to just go through them. At first, I'm going to list them. So we have the input assembler, we have the vertex shader stage, tessellation stages, constant hull shader, control point hull shader, tessellation stage, domain shader. All those ones are related to the tessellation stage. And then we have the geometry shader stage, the stream output stage, rasterizer stage, pixel shader stage, and then finally the output merger stage. So I'm going to actually go into what all of this means stage by stage. So the input assembler reads in primitive data, such as points and lines, from buffers and generates primitives that are used by other pipeline stages. Typically at this stage, what we'll get are, should I say, features or concepts such as primitive topology. So when we're dealing with the input assembler, we're kind of describing what we want our geometry to be. So if we're thinking of Direct3D, we're dealing with 3D geometry. How do we represent 3D geometry in the context of 3D graphics? You may be familiar with this concept of polygons. If I were to draw some shapes like this, you could consider all of these polygons. But there are two kinds of polygons I want to sort of draw your attention towards. So any kind of 2D shape. I have some shapes here, some shapes that kind of represent regular shapes, I suppose, and then like this more irregular shapes, right? But if we focus on this triangle and this, a quad, I'm going to call this a quad. What we're doing essentially at the input assembler stage is that we're describing these fundamental shapes, right? We're describing these shapes using the DirectX API, and there's a particular way that we do this. So, oh, as a side note as well, by the way, a quad can be represented by just two triangles put together like this. That's essentially how you draw a quad. But a triangle shape is more or less like a base. It's considered like a base polygon in this respect, with the quad being a makeup of two different triangle pieces. So anyway, let me see if I can clear the screen. Do bear with me. Alright. Excellent. Primitive topology. How do we use the primitive topology to describe our polygons? So the primitive topology is basically just an enumeration of different kinds of shapes, lines, or polygons. So we could have a line. We could describe a line. And a line is essentially made up of 2 points. If we were to say something like A to B, we have a line essentially. We could have a line list. I'll leave a link to a reference to a really good book. I think I have it just here actually. Funnily enough, just on my desk. What is it? 3D game programming with DirectX11. Highly recommend this book. You can find it at libraries. You can buy it online. This is, I believe, a Frank D. Luna book. This book is comprehensive. But if you were to study this, you will know DirectX inside out. It's that good. Like, this is a really good resource. I very highly recommend this. Just read it as reference even. That's what I tend to do. But anyway, you have your line list. So we have different points. Let's just say we represent our points like this. And then we might have our triangles, right? With triangles with their own corners. And we may even look at lists of triangles like this. And with these primitive forms, we can create scenes, pieces of geometry that are compiled of these 3D geometry that are compiled of these forms. So it's probably common knowledge, even if you're not a games developer, that polygons, these triangle shaped forms, are what we tend to use to build our 3D scenes. And the primitive topology, as I said, is just an enumeration of these forms, such that you define what you define what primitive you want to utilize. Let's say we want to use triangles. We want to use a triangle polygon, and then we lock in, right? So we lock in, we say this is what we want to describe. And why do I say we have to lock into this? Because if we describe, let's say at a high level, I'm using a kind of an analogy for this, we tell DirectX we want to define some sort of shape. Let's say a triangle. We want to define a triangle with corners A, B, and C. And we want to draw lines connecting these vertices, right? Now, how would DirectX know that we want to draw this? What if with the ambiguity that comes with not defining our primitive topology, we could be defining something like this: A to B to C. A to B to C, back to A. So that'd be like CA. So, and to take it a step further, I could say something like D. How does the program know this is what we want to draw? Well, that's where we define our primitive topology, which is done at the input assembler stage. We're basically just telling the program, we're telling DirectX, we want to draw triangles. And I'll just refresh my page. Alright, excellent. The vertex shader stage. So the vertex shader stage takes vertex data provided at the input assembler stage and performs per vertex operations. Operations such as transformations and per vertex lighting. So when you think about this, if you are utilizing transformation, so what is transformation? Transformation is just as the name sounds, or rather, as the name sounds. Transformation, as the word implies, you provide some kind of shape in this example, in this context, and you transform it. So you may translate it. So if you have this square, you can translate it from point A to point B. You can change its shape or scale it, as you can see, so from square A to square B, or perhaps you might want to skew it, for example, as such. So transformation and operations such as transformations and per vertex lighting. So obviously, to see a scene, you need light, right? So if you wanted to describe the sort of lighting that your engine will have, then you may want to describe the lighting or the behaviors of the light on a per vertex basis. So how does light interact if, say, we have light coming in from this angle? How does it react to a vertex here? Or rather, how does the light react when it is met with, say, a piece of geometry from this particular angle? Does the light reflect? Does it bounce? Does it reflect? Does it refract? All these kind of things. Do excuse me. Now, implementation of vertex shaders are performed in HLSL. So HLSL, which is high level shader language. And this is kind of going towards GPU territory, where we are kind of talking to our GPU. Now, a graphics processing unit, a GPU, is not as, I would say, configurable as a standard CPU. You can get into the rabbit hole of CUDA, the rabbit hole of GPU programming, parallel programming, stuff like that. But high level shader language allows us to sort of configure, I would like to use the word configure, certain features or functionality of our graphics processing units, probably more on a discrete level, such that we may have, say, a set of different features offered for a particular GPU. Let's say feature 1 up to feature X, right? Different things that can be done maybe to accelerate a scene, right? Hardware driven acceleration. So we can use HLSL to basically access our features, our feature set, and then we can say, okay, we want these, and then we want to basically apply our features to our scene. Okay, cool. So now we are on the next stage of the 3D graphics rendering pipeline, and that would be the tessellation stages. So why is the tessellation stage important? So we have here, I'll read off my notes to start off with, and then we'll get straight into this. So DirectX11 runtime supports 3 new stages that implement tessellation. It's probably good if I define what tessellation is. Quite a basic concept, a fundamental thing. If we have, say, a surface like this, if we have a square, tessellation could be considered a sort of subdivision of a surface, and as such, effectively, we actually increase the level of detail. So let's say we wanted to do something with this surface. Let's say we have 2 surfaces, surface A and surface B, like this. Now, if we wanted to perform some operation on surface A or B, which one of these surfaces would you consider to have a higher resolution such that we can do more with regards to manipulating the detail of the scene? Yes, so it would be surface A, right? Because we have here 1 and 2 subdivisions. So we can do more. We could say, okay, maybe we can perform some kind of calculation for light to behave in a certain way with subdivision 1, but light to behave in a completely different way with subdivision 2, like that. Whereas, I can just press undo there. Okay. Whereas with our surface B, we only have one overarching face, right? So we can only perform like one operation on it in this particular context. Whereas here we have like 2 levels of detail. So fundamentally, this is the advantage of tessellation. And tessellation here looks at low-level subdivision, as I said, of surfaces into higher detail primitives on the GPU. And in this tessellation stage, we have different, should I say, sub-stages. So we're going to get into all of that now. So we have the whole shader stage. So a whole shader is implemented with an HLSL function. So HL, high-level shader language. So HLSL deals with our whole shader stage. What is the whole shader stage and what comprises the whole shader stage? There are 2 main shaders for the whole shader. So when we're talking about the whole shader, we're talking about 2 things. We're talking about constant whole shader and we're talking about control point whole shader. So a whole shader is invoked once per patch. So a patch is basically a surface constructed by quad triangles or isolines. So as I alluded to earlier, we have our surfaces here. We can consider the face of our surface here, the face of our surface a patch. So I'll go ahead and write surface. And the constant whole shader processes tessellation factors of the mesh. So a tessellation factor, as the name suggests, is a sort of unitless dimension that allows us to control how much tessellation should affect a patch. So if we say if we had our tessellation factor, which I'm just gonna kind of represent by T, if we increase our tessellation factor, let's just say this is hypothetical here, by a factor of n, let's say, yeah, just by a factor of n, then we effectively are increasing the level of detail. So we might do something like this, we might do something like this, or we may continue to do something like this. So if we increase our tessellation factor, we effectively have the prowess to increase the level of detail for our surface. Control point whole shader. So control point whole shader inputs a number of control points and outputs a number of control points. Okay, so there's a citation here about this if you want to go into a little bit more detail than what I wrote here in my notes. 3D game programming with DirectX11. I'm going to leave a link, if I can, to a decent article that on Wikipedia that goes into more information about the control point whole shader. And this is what comprises the whole shader. So again, at a high level, what I just described to you guys, the constant whole shader and the control point whole shader, collectively is a way to affect the level of detail by either increasing or decreasing our tessellation factor. Okay. I'm going to continue here. And it's worth noting that this stage, the tessellation stage, is hardware based. So the tessellation stage is hardware based. So what does this mean? What's the difference between having hardware based versus software based? Okay, so if I start with software based, as the name implies, if you are introducing features that rely on software, then you have a software based feature set, right? So you could argue that you could implement tessellation. Let's say you render a patch, you render some kind of surface, and you could argue that, okay, I could write a program that will increase the level of detail like this via software. And indeed, you could do that. You could possibly do this in a variety of ways. But what are the advantages of having a surface yielding the same result, however, via hardware. What is the difference actually? And on a, no pun intended, but on a surface level, there may not seem to be a difference between a hardware accelerated approach versus a software accelerated approach. But I must say there are probably this ambiguity can be quite considerable. So if you're dealing with hardware based acceleration for your graphics, you basically, let's see if I can make another page for this. You basically have features of your GPU that are particularly configured to deal with the features that you're trying to draw out of your GPU, and this results in performance that mitigates should I say, bottleneck to performance itself. Let's see if I can get this page up refreshed so I can offer a visualization to sort of help support what I am saying. So when you deal with software, for example, to bring it back to software, you're bottlenecked by of course, your CPU, in the sense that your CPU has limitations, right? Your CPU is processing instructions coming in, and you have functionality coming out, sort of thing. And your CPU might be running at, say, 3.2 gigahertz frequency, something like that. So if you're smart, you'll know roughly, probably, how many sort of instructions you can do per cycle. You'll roughly know what kind of performance you get out of your CPU. But then we have this concept of, let me say it like this. This is my representation of a GPU. So if we have our GPU, let's say, for the sake of argument, our GPU also runs at a similar clock rate. But obviously, a GPU is geared towards processing graphics. So a GPU traditionally is not as general purpose as a CPU, in the sense that you have sort of a feature set of functionality, many different kinds of specialized features to render the graphics on your screen. And these features are executed, these features are invoked and applied to our scenes like every cycle. So I'll say, like, on a per cycle basis, our features are executed such that you get the effect on screen of an animated scene. Imagine the sheer fidelity of a game like, I don't know, like Horizon Forbidden West, Super Smash Brothers on the Switch, all these, high definition, high fidelity picture graphics animated on your screen, and we don't really give much thought sometimes to what's actually going on there. The GPU has to be so powerful that it can animate what is essentially thousands upon thousands of pixels, which represent different vertices, different faces, and different surfaces, all on the screen, with color, lighting, shadows, all that kind of stuff, in a fraction of a second, all the time. You see? So GPUs are fast, and thus about the whole thing about hardware accelerated design. Leveraging hardware is an advantage because we get the sheer brute of the GPU to accelerate our scenes. The CPU can do this, but you will be bottlenecked, right? You will be bottlenecked. A CPU is a little bit more general purpose than the GPU. However, CPUs are great at, say, conducting operations, and CPUs are used to, like, control situations like physics and AI. Although you could argue nowadays even the GPU, in its own right, in its own sense, the GPU deals with AI nowadays. But AI, I'm talking about the kind of AI that, say, an NPC in an RPG game will sort of contextualize. I'm not really talking about the whole predictive text ChatGPT sort of AI. I'm talking about AI in a more traditional sense of video gaming. Something like that. Clear the screen. And I shall make another page. Excellent stuff. Where are we on now? Did I go over the domain shader? Okay, so I described the fact that the domain shader is invoked for every vertex created by the tessellation. Okay, I don't think I really dived into this. So I spoke about hardware-based approach. Oh, where's my mouse? So the domain shader. The domain shader is invoked for every vertex created by the tessellation stage. So the thing is, let's say we have our quad. I'm going to change my brush because I like my calligraphy pen. Let's say we have a surface. And let's say we've invoked a tessellation factor and we've increased level of detail to subdivide our surface as such. So if we have, okay, so if we have this surface, and let's actually say like this. So this is our subdivision, right? So our overarching surface, let's say point A, B, C, and D. If these are the vertices that describe our surface, which is this kind of square patch, how do we describe the level of detail of the subdivisions? We could have, say, A1. This is, again, a hypothetical example. A2, A3. And I'm this one out here. Let's say A4. So here we have A4, we have A3, we have down here A2, and we have A1. Hope I've got all the vertices catered for there for this particular subdivision. For the sake of argument, I'll also say A5, A1, 2, 3, 4, A5. So that's just a bit easy to follow through. So where we had 4 vertexes for our patch, we actually have 1, 2, 3, 4, 5 for our subdivisions, right? In aggregate. So the domain shader is invoked for every vertex created by the tessellation stage. So if we consider the subdivisions created here, this is where the domain shader is invoked towards. Okay, so for a quad patch, the domain shader inputs the tessellation factor as well as the parametric UV coordinates of the tessellated vertex positions and all the patch control point output from the control point hole shader. So again, we're sort of defining our tessellation factor, and we're also kind of quantifying the vertexes of our subdivisions. Oops. Geometry shader. So the geometry shader runs shader code for given application with vertices as input and respective generated vertices as an output. Geometry shaders operate on full primitives such as quads as opposed to single vertex operations. So at this stage, what we're doing, rather than doing our sort of per subdivided vertex calculations, we're now kind of going back to our overall surface, and we are performing operations on full primitives, as I've kind of illustrated, such as quads, as opposed to just these single vertexes that are generated by our subdivision approach. Stream output stage. So the stream output stage streams vertex data from the geometry shader to buffers in memory. Sorry. So what I'm going to do, I'm going to make another page here. Anytime we talk about streaming in this kind of context, you want to sort of consider the conduit of data between 2 places, right? Okay, let me get this up. Alright, so let's say we have this. Oh, let me do like this actually. We have a block here, or we have we have some memory. So in our system, we have memory. And with our pipeline, we have the input assembler, which is the first stage of the graphics rendering pipeline, all the way to the output merger stage, which is the final stage of the 3D rendering pipeline. And you could consider memory as a parallel resource across the entirety of the excuse me, memory as a parallel resource across the entirety of the 3D rendering pipeline, such that we can access our memory anytime in the 3D rendering pipeline. At various stages of the 3D rendering pipeline, we'll be utilizing memory. Like this. Okay. And so the stream output stage, as it says here, the stream output stage streams. So that is streaming, as the name implies, streaming. You are literally passing data from stages of the pipeline. So I could say, goodness me, tessellator stage, doing all these different operations, and then we store our operations in memory, right? Memory. And this memory is then, these operations are then streamed to and fro memory, such that we can even pass this information, say from this block, or rather where the tessellation stage, let's just use this bit here. Let's say we need it for this information, this description of our tessellation stage. Let's say we need it for something else somewhere else. So we can then pass our information from this particular place to another place in our pipeline, because we are relying on this particular conduit of memory. So that's kind of the idea of streaming. We're kind of coming towards the tail end of this particular workshop as we hit the rasterization stage. So the rasterization stage converts vector information into a raster image. Excuse me. Primitives are mapped to pixels. Interpolation is utilized per vertex value across each primitive. So when you think about it, this stage gets quite interesting, because what happens is that you're playing a game, right? Let's say you're playing a game, and you're playing a game on a display. Let's say you're PC gaming, and you have a display, as I'm trying to illustrate here quickly, right? And your display has different configurations, but we're going to kind of just draw our attention to, say, the dimensions of our display. So if this is our display, it has certain dimensions, as you can see. And if we have, say, we're rendering our polygon like this, let's say a triangle, we need to make sure we accurately represent our triangle on our screen. And this is considering that many gamers, let's say if we're assuming gamers are using our program, our game, different gamers, people are going to have different displays, different resolutions, different refresh rates. There's going to be so many discrepancies between monitors and TV sets, right? How do we accurately represent our triangle polygon on, let's say, display A? Display A, like this. And that's where this idea of interpolation comes in. Now, the way I like to think of interpolation is sort of a... Interpolation is kind of taking the profile of a sample of data and using our respective sample of data to represent another set of data. So let's say we have, and I guess a simple way to represent this is if we have a data set like this. Let's say we have temperature. of the weather in the UK. So we have anywhere between I don't know, like 0 degrees. Let's say on another week we had 14 degrees. And since we get all 4 seasons in a day here in the UK, we also have 28 degrees, and then we go back to 12 degrees about, and then let's say we have 2 degrees, and then finally 0 degrees again, right? We have this data set. So if we were to consider the profile of our data set, and we may want to interpolate the data. So it's about using only the profile of the data. So we're only concerned with 0 degrees, 14 degrees, let's say it's about here, 28 degrees is about here on another given week. Let's say we go down to 12 degrees, 2 degrees, and 0 degrees. We then have this profile here of all our temperatures amongst the weeks in the UK. And then we have this shape that is formed. This is what you can consider interpolation, right? You're just basically taking the profile of a data set to form another shape of data. I really hope that kind of makes sense. And it is with this kind of approach that we know, okay, if we have a vertex, a set of vertices that comprise our triangle shape, and we have a display of, say, I'm gonna just stick with some small numbers here. Actually, let's make it a bit bigger. 1920 by 1080 display in terms of pixel dimensions, there or about. We want to accurately display our triangle, let's say on some area on the top left display here, but we need an algorithm somewhere in DirectX, some kind of way to know. Let's say we have another display. Let's say gamer A has this 1080p display. Let's say gamer B has another display. Let's say he has a display arbitrarily of 480 by 320 pixels. Now, how do we make sure we reliably represent our triangle in this particular segment on this display, this larger display, as opposed to this display here, which is slightly smaller? We still want to sort of approximate the position of our polygon accurately, and this is where we can use some kind of algorithm that relies on interpolation, such that we can transpose the position of our polygon accurately amongst different displays. So again, rasterization stage. Alright, so clipping vertices to the view frustum can be implemented at the rasterization stage, which in effect can result in culling of geometry that may not be visible to a player in a scene from a particular viewing angle. So there's a few terms there that I want to kind of just go over. Okay. So I mentioned a few terms. I mentioned view frustum, culling, and clipping. At a very high level, without going into much detail, if I can just get my calligraphy brush back. When we're looking at the view frustum, we're basically saying, okay, if we have a scene like this, I'm going to consider this our viewport. So at one given frame of our scene, we have our viewport. But then when we're dealing with the view frustum, you can consider it the area that we can see. So if I consider this our frustum, anything outside of the frustum is clipped. We can't see. So we can only see what is here, right? We can only see what's within the frustum, and anything outside our view frustum is effectively clipped. How can this be sort of useful for us as graphics developers, those of us that concern ourselves with the development of graphics for video games? Alright, so when you're drawing a scene, let's say you have a complex 3D scene. So we're not just dealing with polygons like this, triangles and quads. We're dealing with, and please excuse my drawing of this city. Let's say we have a city. Let's say the city has trees. Let's say there's NPCs in our city. Let's say we also have a skybox to represent a sky with the sun as such. And this is all in like high definition picture quality, 3D scene, fun stuff. If we're playing this game and we're looking at a particular angle at our scene, do we need to see everything? Like if I'm looking at, let's say the viewer angle is pointed towards, the camera is actually pointed towards the skybox. Do I as the gamer need to see then this NPC? And maybe this NPC is like in game units, maybe 500 kilometers away. Does our program really need to bother rendering the modeled information for our NPC 500 kilometers away from our player? The answer is maybe. But if you want to save on resources, then you don't have to actually render your like an NPC character. That doesn't need to be seen yet. Okay, and that's where this idea of clipping and culling comes in. So if we have, say, a cube, another example, and let's say our viewing angle is here, and we're viewing our cube from this direction. The surfaces of the cube pertaining towards what's behind this viewing angle, or what's on the other side of the cube rather. So if we're looking at the cube from this angle, everything pertaining to this surface here can't actually be seen from this particular viewing angle, can it? Because unless the cube is transparent, like maybe a glass cube, we're looking at this surface here. We're looking at this side. So we could write in our framework, in our game engine, a sort of functionality to cull, to clip, to remove the visibility of this side of our cube. And so when it doesn't make, effectively, there's no difference to the scene in the sense of what we see. We still see the front of this, the surface of this cube. But what we're doing behind the hood is that we're saving resources, so we're not calculating and we're not shading, we're not drawing this particular side. So that's where this clipping concept comes in, culling comes into play. Okay, nearly at the end, pixel shader stage. So, pixel shader stage. Rich shading techniques such as per pixel lighting can be applied at the pixel shader stage, and features such as post-processing effects. So when we're talking about like per pixel lighting, I think it's quite a fun concept. If you're dealing with, say, I'm gonna actually bring this to like a 2D realm. Let's say we have a 2D game for the sake of example, and we have our scene for our 2D game. 2D game scene. And our scene is comprised of many pixels, hundreds of thousands of pixels on the screen. We can apply calculations such that we know, okay, if a light source, let's say a light source, hits pixel, let's say for the sake of argument, pixels A through to J, then we also want to say maybe transpose the light to pixels T to Z. So let's say we want to transpose the light from this row, as an example, to this row. Just an example to show how you can apply per pixel calculations at the pixel shader stage. And finally, we have the output merger stage. The output merger stage is the last stage of the rendering pipeline. And what the output merger does is that it basically I'm trying to avoid using the word binds all the stages together, but I could perhaps consider using the word bind. The final rendered pixel color is generated at this stage. This is the final step for determining which pixels are visible. Okay, so what the output merger basically results in is once we have, it's on my eraser. Go back to my calligraphy brush. It's taking a while to load. So anyway, We therefore have our stages: input assembler, vertex processing, a whole shading, pixel shading, everything, and the output merger configures, rather generates our final rendered picture, our scene effectively onto the screen. So this was a quick primer into Direct3D, DirectX, and what the API of DirectX allows us to do. So I hope that this was a helpful tutorial. Although this wasn't a comprehensive technical deep dive, at a high level, we kind of explored what DirectX is and how Direct3D11 allows us to build complex 3D scenes stage by stage via the 3D rendering pipeline. My name is Will, and thanks for watching, guys, and do stay tuned. If you're watching this on Instagram, you see some snippets of my work. If you're watching this on YouTube, you'll probably be seeing more videos in this vein, looking at DirectX11 under the Learn DirectX11 Masterclass series. And also feel free to catch up on the Learn C#11 Masterclass series. If it's on YouTube, you see some information in the description, hopefully. If you want to sign up for that workshop, do so on my website. Info will be down below. Thanks, guys. Have a good day. Bye-bye. See you later.